Welcome back, everyone. And now we're going to look at a bunch of different topics this week, starting with binary and hexadecimal numbers. But first, I just want to make sure that everybody has access to Canvas. This is where all the lecture material is. Make sure you looked around, you look at the syllabus for this course, and always for this semester, Mondays are lab days, and those are absolutely required. You cannot miss a single Monday this semester. Okay, so let's launch into binary and hexadecimal numbers. We looked at binary numbers some earlier, so it's last week. And this week we'll look at binary numbers again and then also look at hexadecimal numbers. Some of you may have already seen this, but if you haven't, definitely you want to read pages 239 to 242 of the textbook, that is Tom Show, and maybe make sure you understand some of the material in this lecture and the next ones. Okay, we saw that data is stored in bits. The word bit comes from the two words binary digits, and so binary digits is sort of abbreviated to bits. A single bit holds either a 1 or a 0, and we hear the term byte a lot more, byte, and a byte is a collection of 8 bits. You might have also heard about kilobits, and kilobits, the unfortunate thing about the term kilobit is it's ambiguous what exactly it refers to. In common usage, a kilobit is 1,000 bits, but it turns out most people use kilobit to actually mean something else. They often mean 1024 bits, which is officially it is kibibits, but yeah, no one uses this, unfortunately. So there are two separate terms to make sure there is no ambiguity. You're supposed to distinguish between 1000 and 1024. You might say that's not a big difference, but it adds up eventually. When you're talking about gigabytes of memory, it turns out, yeah, 1 gigabyte might be different from what you think it might be. Okay, so to show that this is not actually something I made up, it is all true. I have a link here, and I can pull this up for kibibytes. So just like kilobits, there's also kilobytes, and most of the time when we say kilobytes, we mean 1,000 bytes, but almost in every case when we say kilobytes, we actually mean kibibytes, or 1024 bytes, it turns out, which is not just 8,000 bits, but 8,196. Now things are sort of adding up, and it's sort of making a difference. So here is the link. There's a Wikipedia article about kibibytes. Here it is. So it's a multiple of the unit byte. And this article actually lists out all the differences. There's kilobytes versus kibibytes, megabytes versus mebibytes. You probably never heard it, and most people don't use it, but when they say gigabyte, what they really mean is gibibytes. Even I don't use that. I just say gigabyte, and I actually mean 1024 to the power third. There's terabytes, there's tebibytes. Some manufacturers like Apple will use these terms actually just so that they are exact, that they don't sell you short. They'll say when they mean gigabyte, they'll use gigabyte, and when they say gigabyte, they actually mean 1000 raised to the power 3. So some people use the correct terms, but that's actually not that common. Okay. So as we saw last week, if you have a decimal number like 51, we can represent that using a group of bits, and make sure you understand why 51 translates to 110011 in binary. Okay, and we went over how decimal 0 is binary. Let's say we're using 4 bits, it's all 4 zeros. 1 is 3 zeros and a 1. This is the least significant bit position. This is the most significant bit position. You don't have to remember that, but I think you should know how to convert decimal numbers to binary numbers. So 15 is all ones. You add 1 to that, you get 16, which is a 1, and then 4 zeros. Okay. And take a look at this again. Make sure you understand the joke. That is, the joke is that what you see as 100 can be interpreted in binary as 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 0 times 2 to the power 0, which is just 1, and it adds up to 4. Okay, so 100, if it's decimal, then that's 100. But if we say that 100 is binary, then it's decimal 4. Okay, so it might be confusing if it's the first time you've seen it, but definitely you want to make sure that you can translate between decimal numbers and binary numbers. Okay, so there's one more thing that we'll need to look at, and that is hexadecimal numbers. We'll actually see a lot of hexadecimal numbers. If you want to see one, if you take a look at your phone, look in settings and look in Bluetooth and look at your Bluetooth address or hardware Bluetooth address, and that'll be a hexadecimal numbers. That is, it won't just be numbers with 0 through 9 and then going through 10, 11. That is only digits consisting of numbers consisting of digits from 0 through 9, but it will also have the first 5 letters of the alphabet. Sorry, the first 6. That is A, B, C, D, E, and F. So 6 letters. Why do you need these letters? Because it's just easier to look at a hexadecimal or base 16 number system with some way to represent all 16 digits, hexadecimal digits. So we don't have a symbol for 10, so we ended up using A. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15, which, if you remember from the previous discussion, 15 is all ones. I know it's a lot of thinking if you haven't seen this before, but you do want to get used to this as soon as possible. And so make sure you can work between decimal and hexadecimal and binary. I know it's a lot, but you want to get used to it. Okay, so the decimal number 51 is binary 110011. If 51 is actually a hexadecimal number, we usually write this with a 0x, meaning base 16 or hexadecimal. And so this is actually turns out easier to convert to binary, and that is why we actually use hexadecimal. So 5, you can tell from here, is just 0101. Okay, so this 0101 goes here. That's the first part of the binary representation of hexadecimal 51. The second part is the 1. Look over here, it's 0001. And so now we can see that hexadecimal 51, you just take each digit, convert it to binary 4-digit equivalent, 4-bit equivalent, and you get the binary, full binary representation of any hexadecimal number. On the other hand, if you have decimal number, converting this to binary is actually a little bit more complicated, but it's not that bad. You can still do it. And the way to do it is to take powers of 2 and subtract it. So the biggest power of 2 that'll go into 51 would be not 64 but 32. And so this is 1 times 32, 2 to the power 6. And you subtract 32 from 51 and you get, what is it, 15? No, sorry, I have to think. 19. And so 19, so that's a remainder. Yeah, the biggest power of 2 close to 19, that's smaller, is 16, and so you get a 1. And that's 2 to the power 4. in the fifth spot. This is 2 to the power 5 in the sixth spot. And then you have what's left over from subtracting 16 from 19 is 3, and that 3 just you can do that in your head. It's just 0011. So make sure that makes sense. Convert 51 to binary. You should get 110011. This is 32 plus 16 plus 2 plus 1. That should add up to 51. Okay. And as we talked about the last week, there are and or operations. There are more, but those are the nice ones, that simple ones that we will actually end up using this semester when we talk about network addresses. So how does AND work? You take 2 bits, you AND them together, and you get a result which is also a single bit. And so it's a bitwise operation. A 0, binary 0 and binary 0 gives 0. Everything, all the combinations give you 0, except when you have 2 inputs that are both 1 and you AND them together, you get a 1. In some ways, the OR operation is just the opposite. If you have just one operand of the OR being a 1 or more operand being a 1, then you get a 1. If both are 0 and you OR them together, you get a 0. Okay, so coming up next, we have more on computer hardware.